Non-constant acceleration by Lennon Faulkner. Acceleration. So we have two equations for acceleration up there. Force equals mass times acceleration, and acceleration is equal to force over the mass. Acceleration is a relationship between an object and a force being applied to an object that describes the change in an object's velocity at a moment in time. The more force that is applied to an object, the faster the object will accelerate. The less the object weighs, the faster the object will travel in a given time frame. That basically means that if two objects have different masses but the same force is applied to them, they can accelerate at the same rate. And if you have a lighter object and apply less force to achieve the same acceleration. So now we're moving on to work. There are a handful of equations for work. Work is generally defined as a force over a distance, and we can replace the force with mass and acceleration to get work is equal to ma times the distance displaced. Power is work over time. And then we have some longer equations up there that describe work in terms of energy put in and energy external, comparing initial and final velocities. Work is the amount of energy expended over a period of time. If an object initially is at rest and accelerates up to a velocity, it gains kinetic energy. The work done on the system is equal to the kinetic energy gained plus the energy lost to any outside forces such as friction or gain in potential energy. An object takes the same amount of work to accelerate an object that is the same velocity, whether it takes 30 seconds or 1 minute. The kinetic energy of the system increases the same amount over that period. The unit of energy is joules. 1 joule is equal to 1 Newton per meter. If it takes you 30 seconds to accelerate a box up to speed, it will take double the force than it did to accelerate the box over the course of a minute. The same amount of work was done, just over a longer period of time. The amount of work done in a period of time is called power. It is measured in watts, and 1 watt is equal to 1 joule per second. That being said, there is a typo, and I'm not going to redo it. So it's actually the power is the same when accelerating an object up to a velocity, not the work. Okay, here's the conceptual problem. 3 boxes sit at rest on the floor. Each box is identical in size and shape. You and 2 of your friends decide to push them to the other side of the room to make room to play Dance Dance Revolution or something, whatever it is you do that requires boxes not to be there. Each of you push a box. All 3 boxes remain aligned while you all push the boxes. Which box will take the most energy to move across the room? Box 1, box 2, box 3. They all require the same amount of energy because it's the same distance, or there is no way to tell. The answer is A, because the work required to move the box is equal to mass times acceleration times the distance displaced. Since the distance displaced and the acceleration is the same for all the boxes, the relative work required is proportional to the mass of the objects being moved. If the boxes accelerate at the same rate, force is equal to mass times acceleration turns into force equals mass proportionally. So proportionally, work equals m times d, and d is also the same, so work equals the mass. Non-constant acceleration. Since acceleration depends on the mass of an object and the force acting on the object being accelerated, that being said, there are a few ways an object accelerates could change over time. A non-constant force being applied to an object, either by the thing applying the force changing the force, or by the force of friction changing in time. Springs and gravity are both examples of forces that change based off of position. The mass could also be changed, but this is not a super common case. Here are a handful of equations up in the corner that you can look at that are just showing what happens when you integrate an acceleration equation that is not linear. If you have an f of t or an m of t equation that can be plugged into the acceleration equals force over mass equation in order to find the acceleration of an object at a given time, if you integrate that equation, you get an equation that gives you the velocity at any point. Then if you integrate that, you can get a position equation for the object when f of t and m of t. Most of the time, it is simpler to find the work done over the period by integrating f of t and using the kinetic energy to then calculate the velocity of the object. If you have a m of t, you can integrate over the period and find the average mass by dividing it by the period, then using that to find the average acceleration of the object. Quantitative example. Here is another question. If a car is being pushed up a 1-degree incline and has a mass of 2,000 kilograms, you are able to push at 450 newtons of force when you start pushing the car. For every meter you travel, you can push 1 newton less because you are wearing out. Part A is find how far up the hill you can push the car before it starts to slow down. Part B is how far will the car roll up the hill before starting to roll backwards. Part C is find the maximum velocity achieved by the car. Okay, let it sit here a little while, pause the video, whatever you need to do. Step 1 is first let's think about what we are trying to solve for here. We are trying to find the first place where the car begins to slow down. Then we need to find where the car starts rolling downhill. And we need max speed of the car. We have the force put into the system as a function of distance. We also are given the mass of the car and the incline we are trying to go up. Since we have the incline we're trying to go up and we have the mass of the car, that'll allow us to find the force required to move the car at any given time to overcome the force pulling it down the hill from gravity. The plan, step 2. First, we will determine how long it takes until our pushing force is no longer capable of pushing the car up the hill, which is when our pushing force is equal to the gravitational force. Then, we can take that information to find the work done on the car over the period in question. We can also take the height gained during that time to figure out how much energy went into increasing the car's kinetic energy. After that, we can figure out how long it takes the kinetic energy to turn into potential energy plus the added energy over that time frame. Then, to solve for maximum velocity that occurs right before the car slows down, we can use kinetic energy equations to solve for V. Okay, so the equation for the force over the time, or a force at any given distance, is 450 minus x. And then first we find the equation for the force over time, then we find the force required to overcome the force of gravity, then we figure out at what time the gravity is able to overcome the pushing ability. The answer to part A, that you can push the car up the hill 107.93 meters before the car will start to roll downhill. You can see the equation where we figure out the mass relative to the surface, so how much we're actually having to overcome to push the vehicle, and then we set that equal to our equation to figure out the distance we could travel. And then the second part, first we're going to find the energy we put into pushing the car, which is equal to the integral from the start till the slowdown. Then we find how much of that went into potential energy of the truck. After we know how much energy went into potential, we can then determine the kinetic energy gained by the car. We then set that equal to the integral of f of x. After the car starts to slow down, then we can add that to to get our point in the beginning before it rolls down the hill, which is 215.89 meters. You can see the math over here. I took the kinetic energy it has, and then I added the energy we're hitting in, which is the integral of the force, but I re-zeroed it at the spot where it starts to slow down, and then I set that equal to the potential energy equation, which is the distance times the sine of 1 times the mass of the car times the force of gravity. And then for part C, we take the kinetic energy of the object right before it begins to slow down, which should be the max speed of the object, and set that equal to the kinetic energy equation. We find that the max speed of the car was 2.41344 meters per second squared. As you can see here, that's the energy that the car had, and then we set it equal to the potential, or the kinetic energy equation, and then we solved for it. Non-constant acceleration summary. Acceleration depends on two factors, force and mass. Both of these factors can vary in time or in position. Most problems with non-constant acceleration can be combined with some calculus in order to turn it into a far less scary problem, like we did in the second question asked, where we broke the non-constant force into an amount of work over a given time in order to calculate how much energy went into the system. Then, with a few more calculations, we were able to answer the question. The key is taking each problem slowly and trying to think it through as much as you can. Also, free body diagrams are your best friend.